Alright, section 4.2 deals with the basic probability rules, some of which you may remember, some may be new. Many board games involve rolling dice. Imagine rolling two dice, one that's red, one that's blue. We can use the outcomes to develop a probability model. Now, a probability model just lists out every single possibility that can happen when we roll, in this case, two dice. So if I roll the red dice, I can get a 1, 2, 3, 4, 5, 6, right? If I roll the blue dice, let's say I get a 1. And so we have all these combinations, a 1 and a 1, a 1 and a 2, 1 and a 3, 1 and 4, 1 and 5, 1 and 6. So I'm going to keep the red the same, 1, 2, 3, 4, 5, 6 on each column, and then just change the blue die. Let's say the blue became all 2s, and then all 3s, and all 4s, and all 5s, and all 6s. So what we have is the full probability model, all the potential outcomes that can happen when we roll two die. All right, keep this in mind. We'll refer back to this as we go along. So here's a definition to write down. A probability model is a description of some chance process that consists of two parts: a list of all the possible outcomes and the probability for each outcome. The list of all the possible outcomes is called the sample space. So what we just saw in the previous slide is the sample space. It's not the model because it doesn't tell us the probability of each outcome. It just lists all the possibilities. A probability model does more than just assign a probability to each outcome. It allows us to find the probability of an event. Now, an event is any collection of outcomes from some chance process. It could be just rolling 2 3s, or it could be rolling two die that add up to something greater than 5, and there's more than one way to do that. There's different outcomes that we could look for, and each outcome is just an event. Events are usually designated by capital letters A, B, and C, and so on. It's fairly easy to find the probability of an event in the case of equally likely outcomes. So the formula for finding probabilities when it's equally likely outcomes, if all the outcomes in the same sample space are equally likely, the probability of that event A occurs must be found using this formula. The number of outcomes in event A, whatever it is we're looking for, divided by the total number of outcomes in the sample space, all of them. So you've seen the old examples. You have a bag of marbles, and I want the probability of drawing a red marble. I know there's 10 marbles in there, 5 are red, 5 are blue. So probability of getting a red marble would be 5 out of 10, or 1 out of 2. You've done these problems before. We're just putting words to the method. Now, valid probability models must obey certain rules, and I want you to write these down, for definitely the bold part, okay? The first rule: the probability of any event is a number between 0 and 1. It can't be less than 0, it can't be more than 1. It has to be between 0 and 1. This rule follows from the definition of probability, the proportion of times the event would occur in many repetitions of the chance process. The second rule: all possible outcomes together must have probabilities that add up to 1. So all the possible outcomes that happen, when you add up all the probabilities, they have to add up to 1. Anytime we observe a random chance, something has to occur. So they have to all add up to 1. The third rule: probability that an event does not occur is 1 minus the probability that the event does occur. And we refer to the event as not A instead of not occur. We say not A. And this is called the complement of A, and we write it with A with a superscript of C. That's the complement of not A. It means not A. So here it is in definition form. The complement rule says the probability of not getting A is 1 minus the probability of getting A, where A complement is the complement of event A, that is the event that A does not happen. All right, we'll practice this, don't worry. More rules for you, definitions. When two events have no outcomes in common, we say that they are mutually exclusive. All right? Two events, A and B, are mutually exclusive if they have no outcomes in common, and they can never occur together. For instance, I'm either late to school or I'm not late to school. One or the other. You can't be both. I have a job, I don't have a job. You're one or the other. Okay, those are mutually exclusive things. Note that the addition rule here, okay? The addition rule for mutually exclusive events A and B says that the probability of A or B happening is the probability of A plus the probability of B. Okay, that plus sign is kind of important. It's just adding the two because they can't happen at the same time. Now, note that this rule only works for mutually exclusive events. I'll show you another example here in a minute. We will develop more general rules for finding A or B in any situation that works for any event in the next section. All right, so here's an example problem. A four-sided die is a pyramid whose four faces are labeled with the numbers 1, 2, 3, and 4. So like this picture here. Imagine that you have two of them, four-sided die, one blue and one yellow, and you record the number on the bottom of each pyramid each time you roll them. Okay? So like the 4 is on the bottom here. Okay? 4 is on the bottom. So give a probability for this chance process. So then you think through it. Okay, if I get a 1 on the bottom on one of them, I could get the 1 on the bottom of a second. 1 on the bottom of the first, I get a 2 on the bottom of the second. 1 on the bottom of the first, 3 on the bottom of the second. So you can see we're kind of walking through each possible outcome here. Okay, 3, 1, 2, 3, 4, then 4, 1, 2, 3, 4. Okay, so we run through all those possibilities, and we see that there are 16 different possible outcomes. All right, each of them are the same likelihood that it could happen. So we would say because both dice are fair, each of these 16 outcomes will be equally likely and will have a probability of 1 out of 16. Okay? So part B says, what's the probability that the sum of the numbers is 5? Show your work. So then you go back to your sample space and you figure out, okay, which combinations add up to 5? So we said 1 and 4 adds up to 5. 2 and 3 adds up to 5. So does 3 and 2. Those are different outcomes, but even though they have the same numbers, they're in different orders. And then 4 and 1. So the probability of a sum of 5 is 4 different outcomes out of 16, which is 0.25. Right? Hardest part about this problem is just developing the sample space, charting it out, however makes sense to you. All right, so here's another example. All human blood can be typed as either O, A, B, or AB. But the distribution of types varies with race. Here's the distribution of blood types of Black Americans. Suppose we choose one Black American at random. All right, what's the probability that the chosen person has type AB blood and why? Well, look at this table. It doesn't tell us what type AB is, right? So we have to apply one of those probability rules, and it says that all the probabilities of the sample space have to add up to 1. So in order to find the missing piece, I'm going to take 1, and I'm going to subtract the sum of the ones that I do know. I added up 0.49, 0.27, 0.20. Add them up, subtract it from 1, and I find that that probability that's missing in the table is 0.04 for AB, 0.04. All right, and that is why that's what it is, because they all have to add up to 1. Find the probability that the chosen person does not have type A blood. Okay, this is that complement idea. Okay, if the probability that they have AB is 0.04, the probability that they don't is just 1 minus it. So it's 1 minus 0.04, and that gives us 0.96. Now, could you have done it another way? Of course. You could look at the table and you could have added up these 3 that were not AB, and you would get the same answer. Okay, but you need to understand the distinction that if it's a complement, it's just 1 minus the actual event. Okay. Last example, Rolanda has type B blood. She can safely receive blood transfusion from people with types O and B. All right, now having these types of blood, this is a mutually exclusive example. No one's going to have type O blood and type B blood. You can't have both. It's one or the other. This is an example of a mutually exclusive event, and we talked earlier that the rule for mutually exclusive events, you just add the separate probabilities. So find the probability that a randomly chosen Black American can donate to Rolanda. Well, she can get blood from O and B. So I'm going to take the probabilities of O, probability of B, and add them up. And I get 0.69. Easy enough. Because these are mutually exclusive events, I can just add them. Find the probability that a randomly chosen Black American cannot donate blood to Rolanda. Okay, well, if the probability that they can donate is 0.69, the probability that they cannot is just 1 minus 0.69, which gives us 0.31. All right, hopefully that gives you some good examples as you start your problems. Good luck, and we'll see you in class.